Welcome to the presentation of this research titled Reference Class Forecasting to Improve Time and Cost Forecasts, Empirical and Statistical Analysis, presented by myself, Tom, and co-authored by Professor Mario Vanhoucke and Professor Tariq Awam. Project forecasting is a crucial last step in any project management process, since it is the last step to project success and the way to consolidate all the work done in project scheduling and risk analysis. Therefore, several project monitoring and forecasting techniques have been developed in the last decades in the academic literature, amongst which the well-known earned value management technique, but also critical chain buffer management and different artificial intelligence techniques. However, the disadvantage of these techniques is that their outcome is sometimes questionable in highly uncertain, risky and complex environments, and that their performance might be not that good in the early stages of the project, simply because not enough data is available at that point in time. Therefore, other techniques such as the fixed contingency approach and risk-based estimating has been developed. However, they do not take into account the systematic underestimation of project risks. It's actually Flyvberg who for one of the first, observed that there is a systematic underestimation of risks in projects and that this results in cost overruns and delays in projects. He actually comes up with three different root causes for these underestimation of risk. First of all, a technical one. So it means that for many project managers, the project modeling techniques and forecasting techniques are simply too complex from a technical point of view. A solution is therefore in the operations research community to not only develop better, but also more practically relevant techniques. The second cause is political economic. It means that project managers might have a reason to underestimate the risk because it then overestimates the competitiveness of their project. This can only be improved by having a better governance in the company. Finally, there's the psychological component to risk underestimation, which means that project managers typically overestimate their own capabilities or the capabilities of their team, or they systematically underestimate the risk in the environment. A solution to solve this is to have another forecasting technique called reference class forecasting. It differs from the other techniques on the slide because those techniques mainly follow an inside view. This means they are based on subjective estimates of the project managers. This is less the case in reference class forecasting, since here we're going to construct a statistical distribution of similar historical projects and then use this information to correct the project forecasts with respect to the timing and the cost of a project for new projects that we want to start. The research questions in this research are threefold. First of all, we want to know how you can identify similar projects. We're going to come up with different properties that allow us to identify similar projects. We're also going to ask ourselves the question, how much of those properties do you need at the same time in order to really be able to identify similar projects? Can you identify similar projects based on a single property, or do you need to combine different properties? Finally, we're going to ask ourselves, what are the interaction effects that exist between these similarity properties? The main contribution of this research is threefold. First of all, we're going to interview project managers in order to explore which similarity properties are good properties. This is in contrast to existing research, where researchers mainly predefine the properties of similarity based on extensive literature overview. So they use existing properties in the literature rather than to ask project managers what they think good similarity properties are. So in our research, we give the floor to the project managers. Secondly, we're going to do an empirical analysis of this so-called risk underestimation in terms of cost overruns and delays based on empirical projects collected from these project managers. So we're going to ask ourselves the question, is it indeed true that there is a systematic underestimation of risk? And finally, we will investigate the impact of reference class forecasting as a technique to improve forecasting accuracy. First, let me briefly discuss the reference class forecasting technique. It consists of 4 steps, and the first step is you need to identify a relevant class of historical projects. Therefore, we define what we call a property, and this is simply a key project characteristic that, according to us, is a good indicator for the similarity between projects. In other words, if you want to forecast a large project in your company, then you might find that a property that is important for similarity between projects in your company is that it is large. So what you're going to do is you're going to identify a reference class of historical large projects. Secondly, we determine the distribution of the cost overruns and the potential delays in the projects in these reference class. So for all the large projects, you're going to collect this information. Then we translate this into a cumulative frequency in function of the forecast error. We're going to do observations such as 80% of the historical large projects have a forecasting error of maximum 15%. And then we convert this into an inverse cumulative distribution to determine what we call the uplift. An uplift is actually a change that we need to do to a subjective estimate of a project manager. This change might be a decrease of the forecast, but typically it is an increase of the cost or time forecast. We're going to make observations such as if we do a 10% uplift of the budget or timing, then there is only a 5% chance of having a cost or time overrun. In the introduction, I already indicated that we're going to collect data such as the properties of similarity. Therefore, we do interviews with 76 project managers from Belgium and Italy in different industries, and we can say that they have a high experience in their project management tasks. We're also going to use a combination initially of literature interview and input of the participants to obtain these properties of similarity. What do I mean? We've started off with 27 properties that we as researchers have collected from the literature, but then this quickly grew up to 60 possible properties as we allowed during different iterations of the surveys that the participants added their own properties of similarity that according to their experience would be good ones. Then we were able to retain the 10% best scoring properties. And the best scoring properties here means the properties that according to our interviewees are best to measure similarity between projects. And those properties are the type of deliverable, project complexity, the company experience, project definition, the governmental environment of the project, and the impact of employees on the project outcome. Then we have collected also empirical projects. We have collected 52 real-life projects, and we observed that 63% of the projects had a cost overrun of on average 16%. We also observed that the average cost underestimation was much larger than the average cost overestimation. Also, we had to collect important information for our reference class forecasting technique. So first of all, we collected the forecast error both for time and cost for each project. And we also needed to know the values for the 6 similarity properties so that we could categorize these projects into reference classes. Then we started with the actual reference class forecasting technique, and the first step was to construct the reference classes. We did this based on a changing number of properties. First, we only considered a single property to construct our reference classes, so we could do this in 6 different ways since we had 6 different properties. But then we also started to use combinations of the properties, so we made every combination of 2 out of the 6 properties to construct a reference class. We did the same with every combination of 3, 4, 5, and finally we combined all 6 properties in order to construct the reference classes. Once they were constructed, we could then use the technique to determine the forecasting accuracy. Important is to know that in reference class forecasting, you need 2 types of projects. You have the historical projects for which you know the forecasting error, and then there are the new projects for which you want to improve their initial forecast. Since we only had the 52 projects from the interviews, we decided to split them into training sets and test sets, such that the algorithm for some projects knows the forecasting error and then those were the so-called historical projects, while for other projects, the so-called forecasting error was unknown. They were then considered the new projects for which we had to make a good forecast. This is a technique called k-fold cross-validation, which we did with 100 iterations to obtain reliable and robust solutions. This results in a number of interesting findings. First of all, we observed that the average forecasting accuracy improved with 2.41 percentage points if we used reference class forecasting, but some individual properties outperformed this average performance. For example, project definition was a very good property to use when it was used by itself, while governmental law and the impact of the employees actually reduced the forecasting accuracy when they were used independent of the other properties of similarity. The best combination that we have observed resulted in a more than 5% point improvement of the accuracy, and this was the combination type of deliverable with project definition and governmental law. So it's interesting to notice here that although governmental law by itself is not a good property, combined with other properties, it resulted in a high increase of the forecasting accuracy. So the conclusion here would be that reference class forecasting improves accuracy of forecasts, but its performance depends on the properties that you use. The impact of the number of properties is that the accuracy improves as the number of properties improves, and with 5 properties being on average the best, so the highest accuracy. If we added another property, so we go to 6 properties, the maximum number in our research, we saw that the forecasting accuracy slightly decreases. So here we have to take into account that there exists a trade-off between, on the one hand, a higher similarity if you use more properties, because then the projects are actually analyzed in a more detailed way, and because similar projects are only similar if they have same values for different properties. But if you use more properties, then the size of the reference class starts to decrease, and therefore it becomes harder and harder to have reliable and robust solutions. So as more properties are added, we see that there are positive interaction effects, but we have to make sure that we're not using too much properties, as the size of individual reference classes might then drastically reduce. Finally, we also observed some relations between properties. We saw that if you exclude the worst properties individually, then this improved the forecasting accuracy, while excluding the best properties reduced the forecasting accuracy. This might seem as a very straightforward observation, but it again shows that a careful selection of the properties allows us to obtain even better results.